Welcome to Future Tech Unlocked, where we dive deep into the technologies shaping our world. In today's session, we'll be exploring the critical concept of caching in system design. So let's unlock the secrets of making your systems faster and more efficient. Let's break down what caching really is. Imagine this. You're working on a big school project, and every time you need a fact, you have to go all the way to the library to get the book. It takes a lot of time. But if you had the most important pages right next to you, ready to grab at any moment, you'd save so much time and effort. This is essentially what caching does in the world of computing. Caching is a technique used to store a copy of frequently accessed data in a special, faster storage location, so the system doesn't have to go back to the library, or in this case, the database, every time. It can just grab the data from the faster cache and keep things moving quickly. So, caching improves speed and reduces the load on the main system. Let's explore why caching is so important in system design. Imagine you're at a fast food restaurant. If every customer had to wait for their food to be prepared from scratch, the line would move slowly and customers would get frustrated. However, when restaurants prep popular items in advance and keep them warm, customers receive their meals quickly, enhancing their experience. Similarly, caching serves as a temporary storage area where frequently accessed data is kept, allowing systems to respond faster to requests. In our daily online activities like shopping, browsing, or streaming videos, caching helps reduce loading times significantly. For instance, when you visit a website for the second time, your browser uses cached data to load it faster because it doesn't need to download everything again. Caching not only speeds up response times, but also reduces the load on servers. This is crucial for maintaining high performance, especially during peak usage times when many users access the same information. Without caching, systems could become slow and unresponsive, leading to a frustrating user experience. So now that we understand what caching is, let's move on to the different types of caching. Not all caches work the same way. Just like different storage solutions in real life, you wouldn't store cold drinks in your living room, right? Similarly, we have different types of caching to suit specific needs. Today, we're going to talk about three common types of caching: client-side caching, server-side caching, and distributed caching. Let's think about how YouTube uses caching to improve your video watching experience. Imagine you're trying to watch a video and the video keeps stopping to buffer. This happens because your device has to constantly download small chunks of the video from YouTube's servers, which takes time, especially if your internet connection is slow. Now, YouTube uses client-side caching to solve this. When you start watching a video, it doesn't just download one small chunk. It starts downloading and storing several parts of the video in your browser's cache. So even if your internet slows down temporarily, you can still watch the cached parts of the video without any interruptions. This is why, after the initial buffering, the video plays smoothly. Client-side caching helps by storing data on your device, whether it's video files, website assets, or other frequently used content, so the system doesn't have to keep going back to the server. It makes things faster and reduces server load. This is exactly how caching works in system design, by speeding up response times and making sure users have a smooth experience. Now that we've covered client-side caching, let's talk about server-side caching, which is another powerful technique for improving performance. Imagine a popular e-commerce website during a holiday sale. Thousands of users are searching for the same products and checking prices at the same time. If the server had to fetch the product details and prices from the database every single time, the system would quickly get overwhelmed, slowing down or even crashing. This is where server-side caching steps in. Instead of repeatedly fetching the same data from the database, the server stores frequently requested information in a cache. So when many users request the same product or price details, the server can quickly pull this data from the cache instead of querying the database over and over again. For example, websites like Amazon or eBay use server-side caching to serve product details, images, and prices much faster, even during peak traffic. This not only reduces the load on their databases, but also provides a smoother experience for users as pages load quickly. Now that we've explored client-side and server-side caching, let's dive into distributed caching, a powerful approach used in large-scale systems. Imagine a global social media platform like Facebook or Instagram, with millions of users online at the same time, across different regions of the world. With such high traffic, a single server or cache isn't enough to handle all the requests efficiently. This is where distributed caching comes in. Instead of relying on just one server to store cache data, the system spreads the cache across multiple servers, sometimes in different locations. Each server stores a portion of the data, and when a user makes a request, the system knows which server to fetch the cache data from. This speeds up access, balances the load across servers, and ensures the system remains scalable. For example, let's say a user in New York is accessing Facebook. Instead of their data request going all the way to a central server, it might be directed to the closest server, which stores part of the cache. Similarly, a user in London will access a different cache server closer to their location. This setup reduces latency, ensures faster response times, and prevents any one server from becoming a bottleneck. We've discussed how caching can improve system performance, making everything load faster and reducing server stress. But there's a critical challenge we need to address: cache invalidation. Let's consider a real-world example from YouTube. Imagine you're watching a YouTube video that's set to public. Your device caches parts of the video, making it load faster if you want to replay or revisit it. But now, imagine the video owner changes the video's privacy settings from public to private. Without cache invalidation, you might still be able to access that video from your cache, even though it's no longer available to the public. This creates a mismatch between what the system should show and what users are actually seeing. That's why cache invalidation is so crucial. It ensures that when changes happen, like a video going from public to private, the cached version is cleared or updated so users can't access old, outdated information. Now, let's explore cache invalidation strategies, the techniques used to keep cache data consistent with the latest updates happening in the system. There are three main strategies to handle cache invalidation strategies. First, time to live, as known TTL. Second, write-through cache. And third, cache eviction, also known as least recently used. Let's dive into time to live cache strategy. This is the simplest method where cache data has an expiration time. Once that time expires, the cache data is invalidated, and the system fetches fresh data from the source. Let's take the example of BookMyShow, the popular movie and event ticket booking platform. When you're booking a seat for a show, the system holds or reserves that seat for you temporarily, preventing others from booking it at the same time. This reservation is cached for a short time, giving you a window to complete your payment. Here's where the time to live TTL Cash Strategy comes into play. Once you select your seats and proceed to the payment page, the system doesn't release those seats back to the pool immediately. Instead, it sets a TTL of a few minutes, usually around 5 to 10 minutes. During this time, the seats are marked as reserved in the system cache. If you complete the payment successfully within this TTL window, the booking is confirmed and the cache is cleared. But if the payment fails or you abandon the process, the TTL expires and the cache releases the seats back for others to book. For example, if you select 3 seats for a 7 p.m. movie and start the payment process, but get distracted and don't finish the transaction within the TTL, say 7 minutes, those seats are automatically freed up and made available again. Without this TTL cache strategy, the system might either hold on to the seats for too long, causing unnecessary delays for other customers, or release them too quickly, making the user experience frustrating. This TTL mechanism ensures that systems like BookMyShow can efficiently manage seat availability, reduce the chances of double booking, and improve overall user experience. Next up in our caching strategies is the write-through cache. This method strikes a balance between data consistency and performance, making it a popular choice in many systems. So, what exactly is a write-through cache? Imagine you're working on a shared document in a team. Every time you make a change, it's saved immediately, not only on your computer but also on the cloud, so that everyone in your team can see the latest version. This way, the data is always consistent for everyone. In the write through cache strategy, whenever an update or a write request is made to the system, that data is simultaneously written to both the cache and the main storage, often a database. This ensures that the cache is always in sync with the main data store, preventing any stale data from being served to users. This approach comes with a performance trade-off because every write operation is pushed to the main database as well as the cache. It can be slightly slower compared to strategies where data is only written to the cache. However, the benefit is that data consistency is guaranteed, since there's no delay between when the cache and the main database are updated. Think about how Google Sheets works. When you enter or edit data in a cell, it's not only updated on your screen, but also instantly saved to the cloud, ensuring that everyone who has access to that sheet can see the changes in real time. The sheet is always up to date, no matter how many people are working on it at the same time. In the same way, a write-through cache works by ensuring that any changes made to data are written both to the cache and the main database at the same time. This means that the cache is always in sync with the main storage, ensuring that users always get the most recent version of the data. Next up, we have cache eviction, specifically focusing on the least recently used LRU strategy. Let's break it down. In system design, caching is a powerful method for speeding up data access by storing frequently used information in a temporary storage area known as the cache. However, cache storage is limited and can't hold all the data forever. When the cache reaches its capacity, the system must free up space for new data. This process is called cache eviction. Cache eviction means removing older or less important data from the cache to make room for fresh data. Different strategies are used to decide which data gets removed, and one of the most common methods is the least recently used, or LRU strategy. But what does LRU mean? LRU is a cache eviction strategy where the data that hasn't been accessed for the longest time is the first to be removed. The idea behind it is simple. If a piece of data hasn't been used in a while, it's less likely to be needed anytime soon, making it a safe candidate to be evicted from the cache. Let's dive deeper into how the least recently used LRU cache eviction strategy works. Imagine you're using YouTube and watching videos throughout the day. To make your experience smoother and reduce loading times, YouTube stores or caches some of the video data on your device or in its servers. The cache acts as temporary storage for frequently accessed content, so you can quickly rewatch videos or continue where you left off. However, the cache has limited space. It can't store every video you've watched forever. That's where the LRU strategy comes into play. YouTube needs to decide which videos to keep in the cache and which ones to remove or evict to free up space for new content. The idea behind LRU is simple. YouTube will keep the most recently watched videos in the cache because you're more likely to return to them. On the other hand, videos you watched a long time ago are less likely to be needed again, so they are the first to be removed. For example, let's say you watched a video yesterday and YouTube stored it in the cache. Later today, you watch a few more videos. When the cache gets full, YouTube needs to make room for new data. So it looks at the video you watched weeks ago. Since you haven't accessed it in a while, the system assumes it's less important and removes it from the cache. If you try to watch that older video again, YouTube will have to fetch it from its servers because it's no longer stored in the cache. On the other hand, if you decide to rewatch the video from yesterday, it loads quickly because it's still in the cache, thanks to the LRU strategy. This ensures that the system is always prioritizing the most relevant and recently accessed content, making your experience fast and efficient. So, the LRU method allows YouTube to balance storage limitations while maintaining quick access to the videos you're most likely to watch again, optimizing both performance and user satisfaction. That's all for today's session. We've explored caching in depth, covering how it improves system performance, the various types of caching, and strategies like least recently used LRU and cache invalidation. These concepts play a vital role in designing scalable, fast, and efficient systems. If you found today's video helpful, don't forget to like, share, and subscribe. Your support motivates us to keep bringing you more valuable content on system design and beyond. Thanks for watching, and see you in the next video.